We're now going to have an example of a one-way ANOVA using Tukey's Post Hoc tests done in Excel. The example is this. We're testing the hypothesis that gallery visitors' liking for a painting will differ based on its price tag. This theorist is thinking that, oh, if they see a really high price tag on it, they might decide it's a higher quality painting and feel like they like it better. So the experiment was this. There was a gallery and the items all had price tags and people were asked to rate how much they liked each painting. But one particular painting, an unusual painting, came along with a general bit of information about it, as they all did. But the information about the paintings was all identical for everyone who read the information, except on just this one painting, the price tag was varied. And some individuals were randomly assigned to see that this one was a $10,000 price tag. In another condition, they saw a sheet of paper that said it was $1,000. Another they saw it was 100, and another they saw that it was just $10. And so that's what we're looking at. Let's go ahead and begin parsing the problem. I'm actually, okay, what we're comparing are people who saw the $10,000 price tag. And I think I'm just going to copy this and paste it down and then just change the prices. So people who saw the $1,000 price tag with people who saw the $100 price tag with people who saw the $10 price tag. Our dependent variable is the liking for the painting. And I'm going to get rid of all that bold there. And our research hypothesis is people's liking will differ across price tag conditions. And our null hypothesis, we just add that word not. I'm just going to stretch this a wee bit more. Let's add that word not. People's liking, boy, let's spell it correctly too. People's liking will not differ across conditions. And that's for our omnibus test. And there we go. We're asked to describe the comparison distribution, which we know is an F distribution, and we have to stipulate the degrees of freedom. So let's go ahead and gather some information from the problem. I'm going to use copy paste wherever I can here to save time, and we can get our DF calculation right here. I've created a little spot for it. So we know that we have 4 groups, and so our DF between, or the first number in our degrees of freedom, will be that 3. And we know that we can figure out how many we have in total and figure out our DF within a couple different ways. I'm going to start by entering the ends here for each condition. And we could even use a formula for that. It allows us to copy paste. Let's just go count all and let's count our scores. I'll go all the way to the bottom here, guys, so that we can use a copy paste function, even though there are no data in those cells. Now we see our 12 sitting there, very nice. We can put a formula in for our degrees of freedom, even though, of course, it's very easy math. It'll allow us to copy paste. And let's go ahead right away, since we're in here, and get our mean by typing equals average. Again, let's go all the way to the bottom, and that'll allow us to copy paste, because then when we copy and paste it, it'll capture the data all the way to the bottom for the cells that have more in the sample. So now we can just copy and paste these. We'll always check whenever we do something like this, but let's just copy and paste these across our conditions, and let's just spot check and make sure they're good. Did it count everything? It looks like yes, it did. Did the mean count all of the data cells? It looks like it did. And did our degrees of freedom subtract the right number? It did. Now we can get our DF total just by summing those. We don't even need to get our N total. We can just sum our degrees of freedom. You will see that if we did decide to calculate our N total, let's just go ahead and do that. We would be able to subtract 4 and come to the same number. So let's calculate our N. And if we subtract 4, we come to DF within. That's why we can do that same group. And so the degrees of freedom in our comparison distribution is the F distribution with 3, that's our DF between, and 46 degrees of freedom. So to look up the cutoff point, that's what we're going to need to enter to get F alpha. Let's go ahead then and get our tool out. We're going to be using alpha 0.05 with 3 and 46 for the degrees of freedom. So here's our tool. You want to make sure that you've selected F value. Let's change significance to 0.05, enter our 3 and our 46 and calculate. And we learned that our cutoff point is going to be 2.8068. Remember, it's a skewed distribution, so we're always doing one-tailed high. Let's go ahead and let me copy that. I've already not remembered specifically what it was. We can hover over it and copy it. And let's get this plugged in here. There's a couple different places we can plug it in. I'm going to paste it here. And I'm also going to paste it down here in this yellow box where it calls for the F alpha. Let's also put it there, then we'll have it. And I'm also going to mark it on here, even though you're not required to do so. It can be helpful early to just know exactly what we're doing. So let's mark that cutoff point. It's the 2.8. So let's put it right around here. And let's go ahead and indicate what that is. We get to write Fa equals, and we can paste that in there. So now we have our cutoff point marked. We know that everything to the right of that is going to be the reject region. So I'll just put this out here. I'll give it a little formatting so it's a transparent box. Let's just turn up the transparency there. And we know that that's going to be our reject region. All right, we've got that marked out. We're in good shape. Let's go ahead and work on our calculation of F observed. And here's where all our math comes in. You can see that we're doing just some pretty standard formulas that we did in the independent samples t-test. Let's use copy and paste as much as possible. Let's first calculate our deviations, each person's score minus the mean. And in this case, make sure and mark off your $sign so that we can copy and paste this down. And that should do it. I'll go ahead and get the deviation squared right away. And this will allow us to just copy and paste all the way down. I'll just paste to the bottom of the data set, and that will allow us to sum our squared deviations. I'm going to select all the way to the bottom so that we can use copy paste again. Next, we can calculate EVAR. Now, I do have all the formulas written in for you, but I didn't write these in because you've done so much with EVAR. I think you know it by now. You know that EVAR is just sum of squares divided by degrees of freedom. You don't need to have that repeated. You'll recall that the weights, and you'll see this over here, is DF1, in this case of condition 1, divided by DF within. We've got our DF within here, so let's calculate our weight. DF1 divided by DF within. We get the percentage. It's about 20, almost 24% of the degrees of freedom are right here. And then we're just going to weight it a little bit different from the way we did conceptually the same. No, we're going to take and figure out our weighted EVAR. That's what the EVAR W1 means by multiplying our EVAR times weight. So let's do weight times EVAR1. So we're in good shape there. Now let's see the extent to which we can use our copy paste function and use it well, skillfully, to speed this process along. So first off, let's copy these two cells, the deviations and square deviations, and let's just paste them into all of these cells. We can do a double check to make sure it's correct. And it looks like it is. It took visitor 9's score and subtracted the mean, so that looks good. Let's see if we can get these. Let's see how these look. Ah, I see that it's looking pretty good here. That looks good. But we have a problem here. And the problem emerges is because we forgot our dollar sign, but we actually need two dollar signs here. We need to stabilize both the row and the column because we're wanting it to hold in that cell across the row and column. So let's grab this, paste it in here, and see if that improves the situation. That looks much better. We now have our correct degrees of freedom. Let's go on then. It's looking good. So let's copy and paste this here, selecting for these. And let's do the same here for all of these. We'll double check all these in a moment. In the meantime, though, let's copy and paste these, and then we'll do some spot checking. So let's just make sure that we actually did correctly subtract mean from score, and that one looks good. Let's make sure the sum of squares added correctly. It did. Let's make sure the weight did itself well. It did. I'm looking at the cells and their shading to tell if this worked. And let's make sure we did that calculation right. And we did. So we did very well. If it's correct for one, it will be correct for the other one as well. As long as your columns are lined up relationally to the data you're copying and pasting, this all works well. If your columns aren't lined up right, you can make a mess of things, so be careful with it. Now let's calculate our squared deviations. We have 4 conditions here, and we have room for 4 means. We can just copy and paste. Let me see, did I finish what I was doing? I didn't. Let's get MS within. MS within is just the sum of those weighted EVARs. I'm typing equals sum. And we can just go right across here, even though we have text in there. Excel will ignore it. Our MS within is 12.31. Now we can go ahead and we're going to work on our between groups variance. And our first step will be to calculate our squared deviations for MS between, mean square between. Let's get our means first of all. Let's get our mean 1. Let's get our mean 2. Let's get our mean 3. And let's get our mean 4. There are other ways of doing this, but we'll just go manual for right now. Let's get our ends. I'm just typing equals and clicking on the cell. That saves me the risk of making a typing mistake, which you know all too well that that's very possible for me. We're in good shape to continue. Let's calculate our grand mean, which is just the average of these means. We can take and calculate our deviations, mean minus grand mean. And I just made that same mistake. I am so accustomed to going one cell over, mean minus grand mean. And we can put our dollar sign in here. Let's make sure we have it right. I think we have it right. Let's drag that down and see what happens and double check it. And it looks like mean minus grand mean works, so we're good. Let's square these. And let's right away multiply by n before we copy paste. There's our squared deviation multiplying times that little n, our little n's for the group where we use the lowercase n. Copy and paste this down. Let's do a quick double check, make sure we did it right there. That looks good. Let's check and see if that multiplied right. That looks good. So we're in good shape. Our SSN, it's a sum of squares, except it's the sum of squares that we multiplied by n. So it's the sum of this column instead of the squared deviation column. And our MS between is just going to take this sum of squares and divide by our degrees of freedom for between. That's what we're calculating. Equals our sum of squares divided by DF between. And that's our MS between. We're ready to calculate our F statistic. We don't really need to write these down because they are pretty handy. So let's go ahead and calculate. We can see the statistic here. It's SSN divided by DF between. It's MS between divided by MS within. So let's click on MS between, divide by MS within. And there we have our F observed is 8.79. Let's find out, we already have our alpha. So let's plug in our 8.79. We do have a significant omnibus test. If this test was not significant, even if there were planned contrasts, we wouldn't do them. We only do this test if we get a significant result. So this is where ours fell. You can see the 0, 1, 2, 3, 4, 5 across the bottom. The 8 would be further over than that, but it's most certainly in the shaded region. So we need to make the decision to reject HO. I guess I can put our S observed here. I'll just link to it. So our decision has to be to reject HO. Let's go ahead and reject it. I'm going to, whoops, that's not what I need to do. I need to change the font and just call that strike through. And so this is the conclusion that we can draw. We'll just even copy and paste that there and change around a couple different words here. People's liking for a painting. We don't have to say will anymore. We could say differs significantly. Across price tag conditions, and we should put the result of our F omnibus test. F, we put our degrees of freedom. We had 3 degrees of freedom for the groups, and we had 46. Let me double check and make sure I'm remembering right. Yes, 46 for the within. And we put our score, which is only 2 decimal places, 8.79. And we can tell the level we tested at. There we go. Now we're going to go on and remember, all we know from this is that there's some difference in here, but we don't know where it is. So there's really nothing that the researcher can say until some tests are done. Unfortunately, this researcher did not have any planned contrast. And so the most liberal test he can do now is to do Tukey Post Hoc tests, which require testing across every single pair. So what pair do we have? Well, we have 4 conditions. We have condition 1 versus condition 2. We'll have to do 1 versus 3. We'll have to do 1 versus 4. We can do 2 versus 3, 2 versus 4, and 3 versus 4. So this researcher is going to have to do 6 statistical tests. And that's a lot of work. And even worse, that means he's got to divide alpha by 6. That's the Bonferini collection. Let's go ahead right there and get it. We have 6 tests. And so 0.05 divided, whoops, let's get the equal sign, equals 0.05 divided by 6. Otherwise, we have an unfair chance of getting a significant result when it's not really significant, or a type 1 error. So let's start with our very first steps. Let's do group 1 versus group 2. Let's get the means, 1 versus 2. Let's get the ends. And we can, of course, get some of these filled in. We have 2 groups, so we have 1 degree of freedom. And our DF within, let's just get it by summing up those ends we just wrote down and taking away the number of groups, 2 groups. And we'll get our degrees of freedom within is 24. Our grand mean is just the average of these 2 means right here. Boy, they're not very different, are they? And let's go ahead and get our mean minus our grand mean. I'm just doing these manually at the moment. We can square these deviations. We know this is correct because we have the minus 0.125 and the plus 0.125. That's what we always need to see because that's the nature of an average. The score should be equidistant from the mean. And let's multiply by n and do a single copy paste. Let's see here, times the n. We can copy paste these down. And our MS between is just going to be the sum of these 2. We've got a teeny, teeny, tiny number there. We're going to be comparing this number to our MS within as we calculate our statistics. So let's take our MS between divided by our MS within. And we can see that we have just absolutely nothing going around. Our F alpha is going to be using 0.08333 and a 1 and 24 degrees of freedom. So 0.0, I thought it was 0.00833. I think that was it. 1 and 27, I think it was. I might be wrong about that. The right-tailed critical value is 8.11. Let me double check that I wrote these numbers right. Yes, 0.00833, 1 and 24 degrees of freedom. So let me change that. The Bone-Ferrini correction is going to be the same for all of these tests, so you don't need to change that again. It's 8.2671. Let's put that down. Okay. You know, I like to keep my formatting. Let's do it that way. And our decision is going to have to be to fail to reject. This is a non-significant result. I'm going to do one more test, and I'm going to try and find one that might be significant. I think I'll compare this M1 with M4 next. I'm not going to do all the tests because they're all the same, but you do need to do all the tests. I recommend you do it by getting a really nice prototype and including all of the dollar signs wherever you need them, and then see what you can do about using copy paste to save yourself some time. Let's see what we can do here, in fact, with a copy paste. This one is one place I think we're going to need one because we want to always stay right here. So I'm going to put a dollar sign there in front of the I, in front of the column, and in front of the row. And I think now the F alpha is going to be different, but I think I can start here. I'm going to copy that far. We'll see what happens. And now I have to make some changes to the data. Right now, I'm comparing group 1 with group 4. I'm skipping one because I don't want to do all of these and bore you to tears. So let's get mean for 1 in here. Let's get the mean for 4 in here. Let's get our n's for 1 and our n for group 4. And here we have our two groups. We have our 1, our grand mean. Let's see if it calculated correctly. Looks good. We see these look good because we have the positive and the negative. Let's get rid of that bold. I don't know why that's there. And our MS between, it should sum properly. I'm a little bit, yeah, everything looks good there. So we're going to take this big 244 now and divide by the 12.30, and we end up getting an F observed of 19.833. Let's look up our alpha score using 1 and 23 degrees of freedom now. Slightly different score we'll get. And we get an 8.3315. I'll copy that, paste it where it belongs. And we can see here that we definitely have a significant result. This 19.83 is far greater than this 8.33. Our decision has to be to reject HO and conclude that we have a significant result. Now, you have to do 6 tests. I'm only going to do these 2 by way of example, but I'm going to show you how to write the rest of the conclusion. So let's write, first off, let's be clear that we did Tukey's Post Hoc test revealed that people who saw the $10,000 price tag had significantly higher liking for a painting than people who saw the $10 price tag. And now at this point, we would add any other significant findings into this sentence. So we would say, and dot, 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 and dot, 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 dot. So if there were 3 significant tests, we would indicate all of that in one sentence. And then we would go back and put in our means. People who saw the 10,000 price tag, what was the mean? Mean equals 16.25. So now we've told people who saw the 10K price tag had a mean of 16.25, and their liking was significantly higher than people who saw the $10 price tag. What was their mean? Mean equals, and I see that was 10. And I'll put 2 decimal places even though they're zeros. And now in a separate parentheses, I'm going to put the F-score. The F-score was 1 and 23. I think I wrote 24 when I looked up the F value, but it'll be significant regardless. And their score was 19.83. And the probability less than what did we test at? 0.0. Usually what one would do is say less than 0.01. We tested at 0.0083. Let's just say 0.01 because 0.0083 is lower than 0.01. And then we would do the same thing for every test. And then there's just one last thing that we would need to do, and we would need to say something about the non-significant tests. None of the other pairwise comparisons were significant. And that's how we'll conclude that statement and explain those Tukey Post Hoc contrasts. That's the way we would report this statistically, and that's how you would solve this problem.